This is the screencast for section 3.9, example 8. How fast does a flu spread? So at that point, you're probably thinking to yourself, well, fast is a speed, and that's a slope, a rate of change. So yes, this is going to involve derivatives, just not for every piece of this. The spread of the flu in a certain school is modeled by this equation, where P of T is the total number of students infected T days after the flu was first noticed. Many of them may already be well again in time T. Estimate the initial number of students infected with the flu. The initial number of students is the number of students at time 0. So P of 0 is about 5 students. Now, how fast is the flu spreading after 3 days? That is a speed. That's going to be derivative. Well, this is one of those situations where doing a little quick algebra at the beginning is going to help me out a lot in my derivative. Instead of doing quotient rule, my numerator is a constant. So I'm going to change P of T to be 100 times 1 plus e to the 3 minus t to the negative 1 power. So now I can just use power rule and quotient rule in taking this derivative. P prime of t is going to be, the coefficient stays out in front. I'm going to use the outside function, so a negative 1 power, leave the negative as a coefficient, so I'll just make that a negative 100. Leave the inside alone, and now that's going to be the negative 2 power. I have to multiply by the derivative of the inside. The derivative of 1 is 0. The derivative of e to the u is e to the u, and then times the derivative of u, which would be negative 1, turning that 100 back into positive. So now I've got 100 e to the 3 minus t all over 1 plus e to the 3 minus t squared. So that's the messy derivative. At 3 days, I can find p prime of 3 by plugging in 3 to this derivative, and I get that it's about, well, in this case exactly 25 people per day. So in other words, the slope of the tangent line at 3 days is 25 people per day. Part C, when will the flu spread at its maximum rate? What is this rate? Well, I graphed P prime of T in my calculator and found its maximum. The maximum rate occurs at 3 days. The rate is 25 people per day, which is a coincidence. It's the same. I'm sure they did that on purpose. I would have done something different myself, but whatever. They asked you about the same spot that B did. That's fine. The Now Try problem number 51 asks about the spread of a rumor. The spread of a rumor in a certain school is modeled by this equation. I wonder if rumors spread faster than the flu, but where P of T is the total number of students who have heard the rumor T days after the first rumor, or after the rumor first started to spread. Estimate the initial number of students who first heard the rumor. So again, that's going to be P of 0, which is about 18 students first heard the rumor. So there was a whole pile of them and somebody told a rumor. How fast is the rumor going to spread? I'm going to do the same thing I did last time. I'm going to take this denominator and make it to the negative 1 power first before I take the derivative. Now when I take the derivative, I'm going to use the chain rule and the power rule first. Derivative of a to the u is a to the u times the natural log of a times the derivative of u, which in this case is just negative 1. So P prime of T is going to be 300 times the natural log of 2 times 2 to the 4 minus t. All those stayed in the numerator. The new exponent is going to drop this quantity down to the denominator and have a positive 2 exponent. It's asking how fast the rumor is spreading after 4 days. P prime of 4, so I'm going to plug 4 into this derivative equation, and I get about 52 students per day. When will the rumor spread at its maximum rate? What is that rate? So again, I took the derivative equation, graphed it in my calculator, or you could just graph the original and tell the calculator to take the derivative. Found the maximum. The maximum occurs at 4 days, and the rate is 52 people per day. Again, a coincidence that it was asking you about the same values.